VGG16 network, and the extracted features output we have combined with the fine-tuned YOLO version 7 model for object detection, and we have analyzed the efficiency of our detection method for now robots low resolution images, because now camera images resolutions are very low, and it cannot capture a very high resolution images. So detecting the objects in that image is a very challenging task. So this is the overall structure of the now humanoid robot. So in our lab we have now version 6, and these are the different specifications of the now humanoid robot. And its weight is 5.48 kg, height is 58 centimeter, and it has autonomy, that is 60 minutes in active use and 90 minutes in normal use with 25 degree of freedom. So it can do different computation tasks, that is it can move forward, backward, or we have exploration also. Through that it can walk along with the person, and such that object detection, face recognition, gesture recognition, different types of things we can do with the now robot. Its camera FPS is 30. So this is the process in which we have tested. So first, what we did is we have created our own custom data set, and for our data set we have only chosen simple surrounding objects, that are person, ball, bottle, cell phone, and chair. These are the mainly 5 objects that we have chosen, and we have created our own customized data set with almost 380 images for each class, and after that we have labeled and annotated those images into the YOLO format. That is the pre-processing part that we need to do, and then we did some more pre-processing like data augmentation, horizontal flip, and also we have done some rotational changes of the data set. So this is the overall testing process, where the images that is captured to the now camera is first has been done with a feature extraction, that is written VGG16 network. Then we have used it into a modified fine-tuned YOLO version 7 model, and what we did is we have trained all these things into our system, and whatever YOLO V7 weight file we have got, we have used those files into a software, that is choreography, that is specially built for accessing now robot. So in that we have trained those models, and finally we are getting output through the now camera. So this is the interface of the choreography software, and different hyperparameters that we have used is that we have fine-tuned, that is optimizer, confidence threshold, IO threshold, batch size, and learning rate. And with that we are getting different whatever we have defined the classes, that's the models are predicting those things, and this is the overall performance. And we have measured our accuracy in terms of mean average precision, that is a map value, that is map 0.5 and map 0.5 to 0.95. These are two basically parameters that we have used for our object detection, and we have compared our fine-tuned modified YOLO version 7 model performance with other versions of YOLO. We basically tested few models for which basically the file size it was less. So because we need to get the weight file, for which we have to, that weight file we need to train into choreography software. For that we have taken some different models, YOLO version 5 with a map 0.5 value as 83.5%, and we are getting YOLO version 7 as 91%, YOLO version 7 tiny as 83.9%, and YOLO version 8 also we are getting as 86.7%. and with the fine-tuned and with the feature extracted from the VGG16, we are getting an math value as 93.7%. So finally, this work is to use now humanoid robot for the purpose of object direction, and the study focuses on utilizing a customized fine-tuned YOLO V7 network for this purpose. And this technique can be used for the treatment of autism children, through which different objects that were identified now has a inbuilt speech module. So identified object can be actually transferred through the speech to the autism patient. So this will help to human robot interaction, through which autism children can be trained with the surroundings objects. So in future, we can make more interactive speech module. That is, already we have an inbuilt speech module. So we can also make some more interactive speech modules and actions for this purpose. So this is
So a good presentation. So any questions from the audience? Anyone? Yeah.
I'm just asking, so you have trained, fine-tuned the YOLO 7.
YOLO V7.
So for that fine-tuning task, you should have some. So you have some annotated image and everything.
Yes, sir. We have our own customized data set. So before pre-processing into VGG16, we have done some annotations like the horizontal flip with minus 30 degree to plus 30 degree and data augmentation, those things we have done.
Oh, so just for curiosity, so what is the size of the data set to train such a big model YOLO for fine-tuning time?
For in our case, actually, we don't have that large data set, so we have we took around 1900 images.
1900.
Yes, sir. So for each class, around 380 images.
Okay. Okay.
But we can test with large data set also.
Okay. Thank you.
Yeah, okay, couple of questions from my side. So, okay, so for the object classes, right, which you identified, right, and you trained, right, whether there is specific motivation that these object classes will be required for some
Actually, sir,
application?
motivation is to make this thing for the autism children. So as we are doing experiments in indoor conditions, so whatever basic things that are available in our indoor condition like cell phone, bottle, chair, those things are easily available. So to train the autism children, the basic surrounding objects, we took very few.
And what was the response time of the pre-trained network in terms of detection? Have you estimated that? Because that will be the real-time requirement, right?
For training,
Training is fine, but I'm just trying to say for detection in the runtime.
that we have not.
Yeah, that is very important because when you are telling that it is a human interaction,
Yes.
right? It is a real-time thing which is happening, so that you need to take care, right? And also you didn't show that value failed, right? You have only shown that you have to, that means also look into that. That means value failed because those are the issues which you have to take care. And when we tell that indoor has a lot of issues like okay, the ambient lighting.
Yeah, lighting is
One of the most important part of that. So those will be in the next part of the problem, I believe, right?
yes.
Okay. So yes, yeah. One last question, sure.
You showed that you have used the custom data set. Is the data set you made it public or
No, not public. It is actually prepared in our lab. Lab means our students.
Okay, so I was a little bit concerned about what is the authenticity of the data set, like the annotation you have done. So what is the measure to, like what is the process to measure that it is a correct annotation or like your model is not biased like this?
So the question I think is that as the objects are very simple, they have actually used the general intelligence,
Yeah.
but in many of the cases, what he is telling that you need to have domain experts, right, in certain sort of ergonomics or some sort of special cases, right? It might not be good to have the same team is doing the labeling and the same team is doing the training as a normal process should be a little bit different, right? that you should take care in the next part.
Okay.
Yeah, okay, so we thank the speaker once again, right? Yeah, thank you. So now we have the next paper, which is on the, this is on the scene estimation, right? Am I right? The scene estimation for making active decisions. Right? Right, right. So the presenter here is Sabyasachi Moitro.
Good afternoon, everyone. My name is Sabyasachi Moitro, and the topic for my presentation is scene estimation for making active decision. These are the contents. First, introduction, then previous works, followed by our observations, our contributions, then methodologies, results, and discussions. After that, conclusions and references. So, introduction. So, the motivation behind this topic, behind this work is the scene estimation for active decision making is a very challenging problem. And the works done so far did not address the scene estimation problem, that is neither the how the objects are located in how the objects in a scene are located with respect to a camera is addressed, and nor the structure of objects from the data structure point of view is not done already yet. So there is the problem. Our work is to solve this problem. The problem is non-trivial and highly significant, and it is also interesting to many research communities, and moreover, there's a widespread applications in real life. So what is scene estimation? A scene is an image that has many objects with different positions in it, and those positions are localized, and the relative positions of objects in the scene defines the structure. So the localization of objects along with their relative descriptions provides a scene estimation. Now, the meaning of active decision making. We call a decision making active when the decision making is level because the false positive as well as the false negative score is significantly low, and this reliability is very much important in sports, automated vehicle driving, and medical diagnosis and other areas. So we have done a dominant literature review on some dominant literatures from the last 2 decades, 2000 and 2022, and we have also published in a journal. And this based on our literature, this is our work based on the observations of our literature review, where we have devised a method which automatically computes the IU threshold value and confidence threshold value from a given image, instead of providing a fixed arbitrary value for NMS to predict for the final prediction for object detection. So these are observations from the previous work. So there is a chance of information loss for an object or multiple rectangles while using NMS to localize objects, and the object detection methods alone cannot say anything about the relative positions of objects in a scene. It only identifies what the object is and where the object is. Also, as mentioned earlier, the structure of objects in a scene is not studied at all, and the active decision making is not paid attention. So our contributions are to localize the objects in the scene in the least square sense instead of NMS, and to devise a method for the relative positions of detected objects, which defines the nearby and far away objects in the scene. For this, we use the depth information of different localized objects using the shape from sharing information. Then we develop an algorithm for the hierarchy of detected localized objects. After that, we find the impacts of those hierarchical objects, and at last we consider applications for checking the effectiveness of the whole scheme. So methodologies, first the least square estimate for object localization, which is a new approach. So this is a block diagram of or flow diagram of the LS-based approach for object localization. First, we take a scene as an input. Then we perform object detection algorithm in it. In this case, we perform YOLO. After that, from the object detection algorithm, we get multiple detections per object, and from that we detect the number of objects, and after we run the estimation of best possible localized rectangles using the least square sense, and thus we get the final output. So this is the algorithm. So first multiple detections per object, then after that we plot the bounding box center points, then we after that we determine the number of clusters formed from by the center points using k-means clustering technique. Thus we get the number of objects. Then we collect all the vertices of rectangles for an object and get 4 different sets of vertices data. And after that we take each pair of them and feed a straight line in the least square sense. Thus we obtain the ordered lines orthogonal to each other. And step 5, the last step, the intersection points of these required vertices give the localized rectangle, give us the localized rectangle. Thus we obtain all the objects in the scene localized in the image plane, our final output. So this is the diagram. So then we compare this LSS method with the heuristic method. This heuristic method is our device method, which is our previous work. So the first difference is the LSS method is absolutely free from the thresholds for object detection in scene, whereas in the heuristic method, thresholds are adaptively detected using regression model. Second, the objects are well localized in case of LSS method, and in case of heuristic method, the localization is sometimes not as superior as to the LSS method. And if last, the LSS method, there is no chance of information loss for object or multiple rectangles, whereas in heuristic method, there is a chance of information loss for an object or multiple rectangles. So we can say that the LSS method is somewhat superior in all cases. So there is the structural description and relationship between objects and their impacts in a scene. So this is the flow diagram. So we take a scene as an input, then we detect objects using yellow. Then after that, we localize those objects using our least square based method. Then we compute the depths of localized objects using functioning algorithm. And from those computed depths, we create the hierarchy of those localized objects, and after that, we find the impacts of objects from the hierarchy. So this is the steps, and this is the work diagram. So to take the effectiveness of our algorithm, we consider 3 different applications. These are the still images, the final ending scene of a sprint image, and car racing image, and a aeroplane show image, where we find the input the first position and the second position and the third position holders of the respective scenes. And so in conclusion, we gave a brief description of our work. So we have an input scene, we take a scene as an input, then we perform object detection algorithm. In this case, we go from YOLO. After that, we get multiple detections for object localization. Then we perform least square estimate for the localization of objects. Then we compare this least square estimate method with our previous methods. And at last, we done a scene estimation for scene data structure estimation for making aggregation, and at last a few related applications. So these are our references.
Yeah, thank you. And do you have any questions from the audience for the speaker? Okay, so if no, a couple of questions. So when you say localization, right, can you explain that what is the exact localization you are trying to see here?
Localization means, for example,
the localization respect to the specific scene, or localization respect to some object in the scene?
specific. Suppose I have a scene. For example, let's say for this thing, uh, the YOLO object detection algorithm, in this case, we have used the YOLO object detection algorithm. The output of this YOLO object detection algorithm gives the multiple detections per object.
Okay.
And without using NMS, the NMS is used for getting the final prediction.
Mhm.
So we are not using NMS. Instead of using NMS, we are using the for getting that per object per rectangle. We are using the least square estimate method.
So, so you mean that once you cover it with this rectangle, you can take the localization of the.
Yeah, that is the
object.
localization.
That's the localization.
That is the
right?
localization.
So are you taking any sort of geometrical inference out of that, or it is just the information based on the image data?
Geometrical inference.
Geometrical means reference to the different objects, your coordinate positions, or whether, because this can be applied on those applications, right? When you use different types of, okay, that means 3D or multi-view camera options, right? You can use those, okay, those data. So have you tried to extract those also? It is just can you extract those information also, localized coordinates information from the data?
Actually, we have done on a single, a single 2D image.
Okay.
2D image that is normal in normal method.
Suppose how it responds to the different orientations.
Um,
Have you seen the different orientations of the objects? Okay, that means, and still it is localized in a particular
different orientation
views of the objects.
means it is tilted or not.
Yes,
It is tilted
yes,
or not.
yes.
Yes, I have seen it is means we are not using NMS for getting the final prediction from multiple detections for object. We are not using non-maximum suppression method. Instead of using non-maximum suppression method, we are using the LSTM.
So have you compared in the computational, the resource or computational efficiency of this method?
Yes, with that NMS method, I have seen the in our previous work. I have this.
Yeah, this is.
In our previous, we have also published a paper in our previous work that the NMS, that non-maximum suppression method requires two parameters, confidence threshold and IO threshold value for getting the final prediction from multiple detections per object. And those values are arbitrary in nature and fixed. In our previous work, we have devised a method that automatically calculates that threshold values from a given image.
Okay.
So we have done that, but there is one problem that there might be some information loss, means some objects are not covered. Though in the multiple detections for object it is covered, but after using NMS, the rectangle that object is
What
not.
happens for occlusion cases? Have you tried?
Occlusion cases means?
Occlusion cases mean that the object is partially seen in the, okay,
Means half visible.
yeah, is occluded by some other object.
Yes, it is. See
Okay.
this one, for example, suppose for this that car image, that the third car
Okay,
is occluded image.
okay.
Means I have, instead of using NMS, we have used a new method.
Fine, okay. So let's thank the speaker, right? Thanks for the presentation. Yeah, thank you. So now we have the next paper, which is on quantized disentangled representation for object-centric visual tasks. So the presenter is Alexander Cormini, right?
My name is Victor Corciani, and now I present our paper, Quantized Disentangled Representations for Object-Centric Visual Tasks. So let's discuss what is object-oriented approach, and we can see that convolutional neural networks more are biased hard towards texture instead of shape, that picture A you can see. Picture B, you can see that image can be represented as a pack of features instead of the geometric relations. And picture C, you can see here is a breakout game, which is struggle to play by neural networks when the platform just a little adjusted or there is a middle ball. And then picture D, you can see in task to find visual relations between objects. Network also struggles that we need to find if both objects are the same or different. So there is several problems in object-centric approach, and it's called a binding problem that can be divided into segregation, representation, and composition. So representation problem is how is if we represent objects as a pack of features is often approach in neural networks. So when on the scene there are several objects like picture C, there is apple and pear. So we can interpret pack of features as red apple and green pear, or a red pear and green apple. So we need a good representation. The next problem is a composition problem, when we need get the relations between objects and bind new objects into existing relations. For example, you can do this with variables in math expression. And last problem is segregation problem, when we have, for example, two leaf geckos, and there is a zero-shot detection problem. They are both on the same class, so we need an instance segmentation, and they're camouflaged. So we need they have extra similarity, so we need to detect them better. So what can help us on object-centric representations? They can help with visual reasoning and causal reasoning, and in planning and modeling structured environments where we can modeling when we can perform multi-object agent modeling. So we can simulate physical systems, and it's very helpful in interpretability. Also, it can dramatically reduce the data we need to train our models. For example, you can see a lot of points on the sphere that can be represented by one point in the center and the radius vector. So we reduce amount of data. Let's come to individual object representations. That's called disentanglement representation. So we need to represent a lot of a big variety of objects with the same attributes, which need to be expressive, compact, reusable, and we as people, we do this very good. We're focusing on consistent set of attributes like color, shape, and etc. So the brief definition of this kind of representation. So we have a group of actions that can be decomposed. We have world state and representation space, and we can perform action on the representation space such that it's the same in the real world, and each component of action are mapped to a separate component of latent representation, and they are invariant to each other between components. And the Higgins proposed three metrics: modularity, compactness, and explicitness. Modularity means that one component of latent representation can encode only one component of generative factor. Compactness means that one generative factor feature on the image are encoded only one by only one latent feature. And explicitness means that we can linearly decode all generative factors from the latent representation. There are several metrics that are looking almost that have the similar idea when we fix one component of Latin representation and calculate some metrics on others, like the mean values or variance between other values. And the fourth method is just a framework to classify variables. So there is several data sets. We used Clever data set for this. It's a multi-object data set that consists of figures with different shapes, size, material, colors, for position X, position Y. So there is a based architecture on which based our work. It's slot attention. So it's consists of two parts: encoder or decoder, encoder and decoder for object discovery architecture, and encoder and multi-layer perceptron for Z prediction architecture. So slot attention is just a little model. So what about object discovery architecture? It's an approach when we need to represent different objects on the scene on Latin representations with the similar format. And step prediction, we just need to classify all object properties from the scene. The slot attention model means that we sample with trained shared means and variable several slots, and iteratively train with attention mechanism bind input objects into these slots. So after encoder, we got a rich representation that iteratively was binded. So you can see an algorithm for this. So with iteratively binding objects to slots, and we're combine them with gated recurrent unit, and after just drew down MLP, we receive slots. So there is an R architecture, and we propose to add a separate model. There is quantize model that allows to incorporate discrete representations of object-centric embeddings. So we will propose disentangled representation on the embedding level, not on the separate coordinate. So we sample several spaces with discrete embeddings. The number of embeddings is equals the number of generative factors for each property. So 3 for shapes, etc. Then they're forward through the Gamble softmax mechanism. They bind to the slots, and they're after they're concatenated in through, and then they linearly projected to match properties for the set prediction, or they decode it for the object discovery approach. So how it is binded with the Gamble softmax click? At first, we calculate similarities for each slot. Each slot was linearly projected to reduce this dimension that allows us to concatenate vectors later. So we got slot representation. We calculate similarities with each vector in the embedding space. After that, we get a posterior representation by using normalized representation by using softmax function, and then we perform the Gamble softmax trick. It's equation 2, where is G variable G, it's a random sample from Gamble distribution. So you can see that and picture below how it looks after the Gamble softmax. And it has a temperature parameter that we set to 2 it helps to achieve a better disentanglement because each coordinate must be higher for this. So after that, after we receive coefficients, we are performing weighted sum and concatenate it to the one single representation. Also, we added KL divergence loss component. So you can see on image example. We have source image, and we have to change the size of the cylinder to big, and how it performs without Calton and with Calton. But this Calton is reduced the second loss, square root, mid-square root, but overall it's increasing quality of this entanglement. So we achieve state-of-the-art results for set prediction task with architecture that not task specific. So we just improved the potential results, and there is IDSPN architecture that achieve better results, but is very task specific. Also, we experimented with different sizes of latent space. We used only one latent space and with different numbers of vectors in each space when it was several. But the number of when the number of generated factors equals the number of space and embeddings in them, we achieved the best results. So we have qualitative results that you can see. We have one image, and we try to change several properties for the objects. And first column is position x, second column position y, color, and last column is size and shape. So when we are just changing one vector from our remaining space to the Latin representation of SEM, we can modify SEM. Also, we cannot use standard metrics to this task because standard metrics relies on when each property are encoded only by one coordinate, and we have an embedding for this. So we propose to our metrics called disentanglement quality categorical generation backwards metrics. So it's micro and macro. Micro means that we select one space, then we calculate probability. For example, this first space on the picture. We have three vectors in this space, and we calculate probabilities for all our validation data set that this vector was chosen for this property. So for size and material and color, it's just almost randomly with uniform distribution that is good. And for cube, we selected the second vector. For sphere, we selected first vector, and for cylinder, we selected third vector. That means these vectors are binded correctly. And we have macro metric. That means we separate all objects for all properties. For example, big objects and small objects, we create mean and calculate standard deviation, and we have the big standard deviation for in each embedding space for each property. So, but color is not so good. We can see the color is entangled. So we proposed a model that incorporates slot representation, and we can use discrete embeddings to manipulate this system. Also, we introduced metrics. Future work is the adaptation of this approach to real world or real life or simulators, like I2. Thank you for your attention.
Any questions from the speaker, from the audience? Yeah, so one question, can you go to the results? Okay, first, okay, so no, the macro DCQ wave, yeah. Next, yeah, the DQCF. So this one has a more standard variation, right? What's the standard variation? The standard deviation is more varying, right? What's the cause?
If standard variation is high, that means this property is looking or on changing of this vector. So it means this embedding space according to this property.
So it means that means how you compare these results, right, with the existing one.
Yes, our difference is just better results, and also we may to manipulate this thing, but in standard slot attention they cannot do this.
So for a larger distribution of objects, right, that means how this will scale up in any sort of thought process.
For larger objects,
Say numbers also. Say numbers and varying shapes, right?
So we tried this approach on the set data set that consists of a lot of factors like gender, hair color, eyebrows, and others. And it's worked a bit, but not so good. So I think it may be scaled with some additional improvements.
So we thank the speaker for the good presentation. Thank you. The next paper will be, the title is RGB-D fusion based on fuzzy optimization for salient object detection. And the presenter will be Shudita Mila.
Good afternoon, everyone. I am going to present my paper on RGBD salient of RGBD fusion based on fuzzy optimization for salient object detection. So this is the outline of my presentation. So let us first see what is salient object detection. So salient object detection is the method of automatically identifying the most visually distinct or attractive object in an image. These models operate on a psychovisual phenomena of human called visual attention. Usually, how human eye operates or it detects visually important information and discard the irrelevant one, that is called visual attention mechanism. And all the salient object detection models mimic this phenomena. So here there are two types of models exist. One is called simple RGB based, which take RGB data as input, and second one is called RGB salient object detection. So in RGB salient object detection, both RGB and depth data are used as input. So here, though there exists a lot of model based on salient object detection, most of them focus on RGB input only. But their accuracy or the algorithm based on RGB image only, their accuracy decreases or they fail if a object is having very similar in appearance as that of background. So here, if we will consider depth data along with RGB, there we can improve the accuracy because depth data gives some more information, that is your structural information. So that is the main motivation of using RGB and depth for salient object detection. But if we will consider only depth data, if a object is having very small depth value as compared to its background, that may not be detected by depth value only. So there exist two possibility. Either an object may be detected in both modality, that is RGB and depth, or it may get detected in one modality, or it may not get detected in other modality. So if a object is detected in any one modality, their fusion of both the modality information plays an important role to detect all the possible objects present in an image. So this is the main motivation of fusing RGB and depth data for salient object detection. So here we are performing a decision level fusion method where our main aim is to take the object maps from both modality and to reduce the disagreement between them and to obtain a fused map by reducing the disagreement between the input maps and the obtained fused map. So for that we have used fuzzy divergence measure. Here the main notion behind using this fuzzy divergence measure is because it is well known to measure the dissimilarity between between two maps. So here our main aim is to reduce the dissimilarity between input maps and to obtain the optimal field map. So this is our proposed framework where we have taken two modality information. One is RGB, second one is depth. From these two modality, we are generating a set of maps which we called as prior maps. After I will discuss how we are generating these prior maps. Then after obtaining these prior maps from both the modality information, those maps are fed to a optimization model. So in the optimization model, based on these input maps, we are estimating the parameters, and those parameters estimated from the input maps are fed to the fuzzy inference system. So here in this fuzzy inference system, or the main function of this fuzzy inference system is fusing the input maps, and after fusing here, after defuzzification, we are obtaining a set of maps corresponding to a set of parameters of them. Again, suppose we are obtaining n number of maps. We call them as initial map. So from that n number of maps, we are calculating what is the fuzzy divergence between the obtained map and all the prior maps. So the map corresponding to which, again here, we are minimizing the fuzzy divergence because as I told, our aim is to minimize the disagreement between the prior maps and to obtain an optimum fused map. So here we are minimizing this fuzzy divergence measure, and we are doing the map corresponding to which this fuzzy divergence measure will be minimum, that will be taken as the optimum fused map, and the parameter corresponding to those optimum fused map are called optimum estimated parameters. So now let us see the generation process of different prior maps. Here we have used any of the existing object detection technique can be used here. Here I have used one of our published method cited here for generating the prediction map from both the modality. Here we are taking the input image both RGB and depth. Suppose first I'm taking the RGB. For that we are using or finding out what is the proto-object partitioning corresponding to the input image, and to get this proto-object partitioning, we can apply either mean shift or any alternative quantum map which gives the boundary. So after getting the proto-object partitioning, we are generating a set of operator mask. For this, I have used this method. So after getting a set of operator mask and the input image, and applying those masks on the input image to calculate the and performing center surround operations to get multi-scale center surround maps. And after normalizing them, we are getting the multiple object regions here. This same method we have applied for both RGB as well as depth modality. So here in this example, we can see, as I told, our main aim is to detect the maximum possible object. If an object is not detected in RGB, that may get detected in depth. So in this, for this input image, you can see this object is not detected in depth modality, as it is having very small depth, whereas it is detected in the RGB modality. Similarly, for this object, you can see if these are having very similar in appearance to that of background, here they are not detected in this RGB modality. However, they got detected in the depth modality. So here, after fusing this two map and the other prior maps, this is our optimum fused map where we can see both the objects are detected in the final image. So the next one is the next prior map, that is for distance map both in RGB and depth. So here to get the distance map, again this is based on the notion that background is usually described by features like high area ratio and widespread close to image boundary. So based on these notions, we are defining a way to measure taking the location information as well as the spatial extent of a proto-partition. Taking the position or location of a proto-partition, a measure is defined given by this, where this P is the center position of a proto-partition and C is the center position of the whole image. And this DC is the distance between the center of the image and to its kernel. Similarly, taking the spatial extent into consideration, we have defined this measure that takes into account the spatial extent. That means if a proto-partition is spatially extend more, that weight will be less. Again, this is based on the notion that always background partitions are spatially more extent as compared to object region. So therefore, we are applying smaller weight to large proto-partition. Then combining those two, that is based on location and spatial weight, we have defined the final distance measure as this one. The last one is for the depth ratio map generation. Again, this is based on the notion that usually background regions are considered to have high depth value. High depth value means they have large area, so their difference between the minimum depth value and maximum depth value will be high as compared to the object region. So taking that concept, we have defined this ratio. Again, for the if this ratio is more, that means there is more probability that proto-partition belongs to background region. So like this, we have generated 5 different maps. Then to combine those maps, we have used the Magdani fuzzy inference system. Because its simplicity, we have chosen this one. So the fuzzy inference system consists of these 3 steps, that is fuzzification, inference, then defuzzification. So for fuzzification of each map, we are using 3 input membership function. That means again here we have selected Gaussian function as input membership function. So here and the parameter of this membership function is mean and variance. So corresponding to one prior map, 3 membership function we are taking, that is lower, intermediate and higher. Again, this defines the saliency range of each prior map. So corresponding to one map, if we are taking 3 membership function, here we can say again for each membership function we have 2 parameters to be estimated. So corresponding to one prior map, we will have 6 parameters to be estimated. But here for this lower and the higher one, we have taken the mean as 0 and 1 respectively. That's why corresponding to one prior map, we have 4 parameters to be estimated. Similarly, as we have 5 number of prior maps, total we have 20 input number of parameters to be estimated. Similarly, for the output membership function, we have taken the same 3 numbers of membership function. So for the output map, we will have 4 parameters. So total 24 number of parameters we are estimating here. The second step in the fuzzy inference system is rule evaluation. So for that, we have defined few rules like this based on the number of membership function we have taken, 3 membership function we have taken. Then we are combining them by using min, max, min inference and defuzzifying to get the output fused map. So this is the equation how we are getting the output fused map. Like here, this I1 to I5 represent our 5 prior maps, and this A5 represents the output map we are getting after combining them with, from the fuzzy inference system. Like this, we have taken suppose n number of input parameters corresponding to each set of 24 parameters. We are generating fn number of fused map, and we are calculating what is the fuzzy divergence between them, and we are minimizing that fuzzy divergence to increase the similarity between the output fused map and all the input parameters. So for the map for which this objective function will be minimum, that will be our optimum fused map. So this is the quantitative evaluation result. So as I told, our main aim was to detect all the possible object or multiple objects. That's why here we have considered the data set having multiple objects only. Again, to compare with the deep learning based technique, we have taken the pre-trained model. They are trained on pre-trained model where they are trained on the benchmark salient object detection data set. So here we can see in most of the cases in multiple object data set, our method gives better result as compared to state of the art technique. This is the visual comparison of our method with the state of the art method. Here also it can be observed in our method, maximum number of objects are detected as compared to other state of the art methods. So here I would like to conclude this presentation. So this paper proposes a novel RGBT fusion method for SOD tasks based on fuzzy optimization concept. The experimental results show the efficiency of our method in detecting multiple salient objects. So these are the references. Thank you.
So any questions from the audience? Okay, so if no, that means I just want to know what was the basic motivation of not going into deep learning and keeping it in the fuzzy?
Sir, actually our aim was to apply this concept in robotic application. Again, that is only in the industrial robotic application. So the main problem exists in deep learning.
Because fuzzy has a lot of parameters you have to fine tune in between, right?
Like this, in the industrial environment, which I experimented in our for the robotic environment available in our lab. So whenever we are varying the illumination or whenever we are varying the environment, there even if we are training the system, the accuracy is decreasing by varying the environment. Again, if we will aim only in the industrial environment, it is not always possible to generate the huge number of annotated data required for deep learning.
So that was one of the pitch that what you
That was the
wanted.
main motivation for going for this classical technique. The second one is, as I saw in the result, when
So how does your, that means your complexity of the problem scales up, right? When you have multiple objects and larger scenes, have you tried it?
actually, what I have tried, like where if there are multiple objects, like here you can see in the image already 7 objects are there. That does not much affect the complexity. But yes, if I am increasing the number of membership function and the rule evaluation, number of rule evaluation, then the complexity will be.
Yeah, that will be sure.
But what I have experimented, like here, I have taken almost 7, 8 rules. Then I increased them to like 50. But when I kept the rationale behind designing these rules, like here, as you can see, when this is lower, based on some rationale, we have designed this. So even if we are increasing the number of membership function, but keeping the rationale same, the output we are not getting much difference. But if we are drastically changing the rationale, then there will be effect on the output. So that's why even if by taking 3 membership function and increasing the number of objects, we are getting the optimum.
Okay. So we thank the speaker for her presentation. Thank you, once again. So I'll call upon the presentation of the next paper, whose title is after so F4 drive detection of derivable area for autonomous vehicles. And the presenter is Ujjwala Patil. Yes.
I am Ujjwala Patil with my collaborative work with a team from Day2 Technological University, Karnataka. I'm here to present a work on the detection of drivable area in autonomous vehicles, affordance map to affordance map. What is affordance? Affordance, if we go through the wiki definition, affordance is a estimation of potential action possibilities for an object in an image. So if I am holding this pointer, I'm afford to hold in this way only. I'm not afford to hold it in this way. This is a potential possible way of action. And if I apply that to a autonomous vehicle, I have to give the autonomous vehicle what is the affordance of that vehicle being on the road, on what part of the scene it can move, on what part of the scene it should not move. So that affordance estimation we have experimented in this small work. Much things has to happen at this is a very preliminary stage what we have applied the affordance. Most of the researchers in the robotic community has used the affordance for the scene perception for the bot movement. So we tried that for the autonomous vehicles. This is the plan of my presentation. I'll start with the motivation, what people have done in the literature, our contribution, proposed work, then I conclude my presentation with results and discussions. I think you have seen this, still I'm just motivated by this and I just want to play this for you. 1 minute, I just want you to listen to this. This is BMW test vehicle moving. So this is a BMW test vehicle. When it is moving in a night, somebody had misunderstood, and this is a very, I think all of you have seen this. It's autonomous vehicle future. And if anybody asks me what is the scope of autonomous vehicle in Indian scenario, the answer is very ambiguous because it has opened up so many research avenue. We don't know the end result where we may land up. But the thing is, it has opened up so many research avenues. So when we think of autonomous vehicles since last 8 to 5 years, it is not the recent technology what we are envisioning with this generation of researchers. It had been started long back in 80s or 18th century. Look at the picture what in online what I had kept it over here to align my motivation to take up the affordance. So this is already have been envisioned by our ancestors or our elders. So now we are working towards to make it more reliable, more reality in the Indian scenario. Is it safe to get relaxed on Indian scenario? The answer, as I said, is very ambiguous. Only thing is we have to look at the research avenues that has kept open for us in the autonomous vehicles. When I talk about the autonomous vehicles, unimodality data or the perception using the unimodality will not suffice the problem. It should have a different modality. And when I talk about the different modality, it could be a depth sensor, it could be a radar, or it could be IMU, it could be multiple sensors. For that to sync everything on a single vehicle, it will have its own challenges because I have to have an optimized instrumentation to handle that means to sync all the data for the scene, and we have to register all the data, we have to process it for the scene perception. And whenever I think of a multiple modality, I have to rely on the skilled personnel, I have to rely on the in situ measurements, at least for data capture during the training process. Then I can deploy that on an autonomous vehicle. Instead of that, if I have over RGB, can I generate a affordance map? And definitely the unimodality inference will not have that proficiency. I should extend that to multimodal scenario and in the harsh environment scenarios. So people have already started using this affordance for different use cases, as I was telling. So this is one use case where the people have used to estimate the affordance for holding the bat in the tennis or cricket, how to hold the bat properly. And that is used for the evaluation of the players who are representing a national level athletics. And this is one more work where people have used to estimate in a closed room scenario for the what is the walkable area, what is the affordance for the walkable area, what is the affordance for sittable area, what is the affordance for sleeping area. So these type of works have been done, as I said, for the robotic research community, and we motivated from this, and we thought of applying for this for the autonomous vehicles. So people have used this recently for the autonomous vehicles, but the only thing is they have not addressed the problem of occlusion. Whenever there is a vehicle, or whenever we have to we have to estimate the affordance for the road or the drivable in front of that occlusion, those people have not addressed this. Towards this, we have proposed our affordance map for the autonomous vehicles. So we propose a pipeline to generate the affordance map for the drivable scenario. We generate a affordance map to detect the highest probable area for the safe drive of the autonomous vehicle. And we also generate the surface normals so that we can get the inference of orientation of that area. So that is, these are the two mid-level cues, that is the depth as well as the surface normal we are giving to generate the affordance map, and using that affordance map, we are segmenting the drivable area for the autonomous vehicle. We propose a technique for obstacle dodging. This obstacle dodging is the prior work to the lane departure warning system. So we are connecting, or we are detecting the mid of the drivable area where the autonomous vehicle has to move without crossing the lane. And we also perform the comparison with the state-of-art techniques as well as available data set. We have tested our algorithm performance with various data set to demonstrate the generalizability of the framework. So this is the RGB input and the depth estimation pipeline we have used, a recent depth estimation algorithm we have used. And then we could get the depth map, and this is used for the normal estimation, surface normal estimation. Usually the surface normals are used for the orientation and the geometric information. Those two are given as a clues, mid-level cues for the segmentation. And we have got this as a drivable surface area. Basically, it's a segmentation, but with these two clues, we could complete the pipeline for the affordability for the safe driving of autonomous vehicle. So we have used the recent Google research segment depth map estimation framework. This is the nearest for the depth estimation, and this is the loss information what they have used. So this is the RGB, and we could get the depth map using the Google research recent state-of-art technology, recent or state-of-art framework for the depth estimation. And this is the gradient computation and the normal vector calculation, and we have got the normalized vector for the surface normals, and we use this for the final affordance segmentation so that we can infer where the vehicle has to move. And in this drivable area, this line has to be, the center line has to be detected so that any line warning system, we will give some margin for the deviation. If the vehicle is moving out of that margin, then the lane departure warning system has to get activated, and the controlling room should get the buzzer. That is what the complete pipeline of this work is. So we have experimented this small work in the cityscape dataset. It has been captured across 50 cities and 30 classes it has got. Good variance data set it is. And we have used the last function, and this is the different images we have chosen from the cityscape data set, and we have tested with that given RGB image. So this is the depth and the affordance map estimation using the depth using the deep lab B3 plus, and this is the unit depth, and these are when we compare these two unit and the depth lab B3, this is the Google research depth estimation, and then that depth estimation or the depth map is used for the surface normal estimation. And when we have compared these two, the depth estimation or the affordance map is more accurate with the Google research framework for the depth estimation. This is the obstacle dogging. We could initially we could not track the line, and this is a ego vehicle. And in few of the outliers we have observed, and the center line or the central line of the center marking of the line is detected through the autonomous vehicle for the safe and autonomous drive. So this is cityscape data set, and that was the cityscape data set, and this is the KP data set also we have compared, and this different data sets we could experiment to test the generalizability of our framework, proposed framework. This is a prototype of the, this is the result of our prototype, whatever we have just started to work on in the domain of autonomous driving. We could compare the quantitative, we could compare the framework performance in different depth estimation unit and the lab deep lab P3, and we had given only the RGB as a cube, only the depth as a cube, only the surface normals as a cube, and surface normal and depth as a cube. Whenever when we compared this, we could see the MIOU for this combination, that is the lab 3 plus framework for the depth estimation, and the combination of depth and surface normals whenever we gave, we could get the maximum MIOU. This is experimentation what we have done, and the future work is we have to test it through harsh conditions. We have to test it through different occlusions. We have to test it through different surface writings. Then only we can say that yes, it is safe for deploy on the autonomous vehicles. Thank you.
Thank you, ma'am. So any questions from the audience? This?
Just check whether I could play that first video.
So I have a couple of questions, ma'am.
Yes.
This. So you have shown an auto encoder, right, in your
Yes.
pipeline. So
Yes.
it is only for the reduction of the feature space, or it has any other utility? Yeah, if we look into the, I think at the last part, you show that in the pipeline you show an encoder, right? No, the last before the contribution, yeah, just before. No, after this, I think you show this, yeah.
Yeah, this is that is
No, then you show the next one, I think. Next one. Yeah, this one.
Yes.
Yeah, so you use an encoder. This is just for optimizing the feature space,
Yes.
and reducing the feature space, right?
Yes.
Okay, that means I just am curious that means how you define this particular drivable area, that okay, there is any particular way you are defining in terms of feature?
No, sir, I'm using the differentiator from the land and the road for time being.
Okay,
Because I assume that it is a structured road scenario, and the differentiator between the land and the road would be my one of the feature
okay.
to set my boundary
So
for
nothing on the terrain or something, right?
it
Okay.
is on whether it is in the drivable area or
Yeah, because that's the problem I was trying to guess, that whether you can do it only by image.
no.
But Okay, because terrain condition is basically done with those depth sensors.
Yes, that's it.
Right? So you can create a depth image, but whether you can create the depth surface, because it's more important to know the surface, right? And what are the resolutions you can do this? Have you estimated resolution of the depth?
The resolution is, 24 bit.
No, resolution in terms of the physical depth. I mean, how much you can resolve? That means whether you can resolve a distance of maybe 1 feet or a distance of at least 5 feet.
No, we could do it for, 2.2 feet. 2.2 feet.
So at least you can differentiate the graduates, you can differentiate a depth, okay,
Yes,
which is as far as 2.8.
yes, 2 point.
Thank you.
Thank you.
Thank you, ma'am. Yeah. So we have the next presentation, which is revealing the unseen, single stage attention based occluded object detection model in remote sensing imagery. And this will be presented by Nandini Saini.
Good evening to everyone. I'm Nandini Saini from IIT Jodhpur. Here presenting my paper, Revealing the Unseen, a single-stage attention-based occluded object detection model in remote sensing imagery. So the agenda of the presentation is as follows. First, I will explain the introduction, then some part of the literature survey, then the main contribution of my paper and the methodology, and the following data experiments along with the results. So, in recent years, deep learning models are increasing a lot, and they are getting the success in the object detection from the images which is captured from the ground truth. So these are called as natural images. So these particular methods are not directly transferable into the remote sensing images due to the multiple kind of challenges, because remote sensing images is captured through the satellite, through the drone, or any kind of aerial camera vehicle. So these instruments are captured the overhead view of the area. So these are include the multiple challenges like the clutters of the objects, occluded objects, object scale variation, and the illumination. So the one kind of challenge I will handle in this research work. So the challenge is the occlusion. The occlusion refers as the objects are obstructed by the other objects. So occlusion can divide into the any kind of category. So like occlusion is due to the man-made objects, like due to the building shadows. So these are the man-made, and other kind of occlusion like the environmental occlusion. I define environmental occlusion is like due to the rainy weather, due to the fog, due to the clouds. So these are categorized under the environmental occlusion. So these occlusions are due to these occlusions, the image quality of remote sensing imagery will be reduced, and it will affect the object detection performance also. So here I have for the introduction, there are some images which include the environmental occlusions. First is the foggy, second is the rainy, and third is the cloudy. So in the literature, the literature is divided into the two main categories. So deep learning algorithms are applied for the alien image object detection through the multi-stage detector and through the one-stage detector. In the multi-stage detector, there is a two-step process. In the first step, we need to identify the region of the interest, and in the second stage, we will detect the objects and the corresponding class. these multi-stage object detectors suffer from the means these are the highly these are the computationally expensive and also low inferencing speed. And in the one stage detector, in one step we will detect the objects and we will classify and localize the objects into the respective class. So in the occlusion, handling the occlusion, there are two kind of methods are introducing in the literature. First is the image enhancement based method, and second is the deformable part based method. In the image enhancement, we can the researchers have added increase the resolution of the image to handle the occlusion, and in the deformable, the model will learn the part based the part which is not occluded by any kind of objects. So learning is depending on those objects which are not hidden by any other objects. So these are the literature survey, but these survey are not includes the environmental kind of occlusion. So the motivation behind of this work is this. So the problem statement is that our work will take input as an aerial image with three kind of occlusion, and as an output we will detect the known categories of the image in terms of the bounding box and respective label of the class. So in this work, I have three main contribution. The first contribution is I will introduce the image adaptive framework, which will focus the most significant reasons using the attention-based mechanism, so that the model will learn the most important reasons, so that it can classify the objects correctly. And to the aerial imagery contain the overhead view, so there is a multiple kind of scale variation. To handle that scale particular variation, in the last detection head, I will add the multiple heads so that I can detect multiple scale of objects like small, large, extra small, these kind of objects. And the experiments also added with the three kind of occlusions. The main architecture of the diagram is as follows. So here the main components of the architecture is the backbone of the network, and which is the which is the feature extraction part, and the second is the neck, which is the fusion of the features, and third is the head, which is provide the detection of the objects. Here, the main contribution is the attention-based feature enhancement and the hybrid data training. For the like here, I have not used the simple convolution network. Here, I have used the depth-wise convolution. So, in that particular depth-wise convolutions refers to the convolution operation applied on the independently of the channel. So, and along with here, I have used the silu activation function so that the convergence of training will be increased fastly. For the hybrid data training, I have added the all three kind of occlusions images, foggy, rainy, and cloudy. So randomly, I have taken the 40% of the images from the batch and apply the augmentation of related to the foggy, rainy, and cloudy, because there is no such kind of already available data set which will include these kind of occlusion. So we need to add the synthetic data set. So for that, I have performed these kind of steps. So for the model training in the particular batch, the 40% of foggy and cloudy and rainy image will be generated. So these kind of batch will go through for the training purpose. Now for the experiments, I have used the standard aerial image benchmark dataset. The name is a NWPU-VHR10, which contains the 10 category and the total images is 800. The categories are these like aeroplane, ship, storage tank. The experiments will conduct into the three kind of settings, the three kind of occlusion which I told before. These are the results which I have performed. So first, I have taken the baseline as a Euro V5 network, and I compare with the baseline network. And in the R network, I have performed, and these are the particular result. The bold letters are signify the R models improvements. So these are the pretty good in the settings B. And setting A and setting C for the sum classes is good, but for the sum classes is not that much improvement due to different characteristics of the each classes. And the overall results from these, the overall results from the R network is the as follows. For the if I test on the normal data set, then the R model will give the 73% MEP, and for the cloudy it will give the 67.4%, and for the foggy and the rainy it will give the 61.9 and 68.4%. So after for that, if I will try for this network to deploy in the real time environment, I need to analyze the inference time and the computational complexity also. So for the computational complexity, I have used the GPROX, which is used for which is the one of the parameter to measure computational complexity for the deep learning neural network. Here I have got that the inference time is the 6 millisecond for the for one image, which is the total time of take input and take output for the object for the image. And the complexity also the less comparatively the baseline. These are the some visualization results. So like the aeroplane, the left side is shown as the normal image, and these are three different cloudy, foggy, and rainy images and the detection results. So there are these results for the some various ports, like for the normal image, for the cloudy, for the foggy and rainy. Here we can see that in the foggy image, tennis courts are not identified by the R model, because the occlusion percentage is so high comparatively the other occlusions. So the detection is also depend on the types of the occlusion. So for the conclusion, here our model is the lightweight and the image adaptive single stage model, and the inference time is less, so it can be deployed for the real time also. And additionally, in the future work, we will cover the different kind of other occlusions, like the main-made occlusions and the inter-object occlusions, which define as a one self-object is abstract the self that particular objects. And the additional experiment is that here I have used only one kind of data set because I need to generate the synthetic data set. So I will to generalize this particular method in future, I will add the numerous kind of aerial image data set which is available, and along with that for the real time deployment, to build the trust on the results, I will add the explainability also in the model. These are the references. Thank you, everyone.
So any questions for the speaker, of the audience?
So the experimental part, I might have missed something. So when you present the result of your model versus some of the baseline models based on yellow and yellow transformer. So you spoke about augmenting the training images with the three different kinds of occlusions or something, so the deviation. So For the baseline models also, I hope you did the same kind of thing and then what we are trying to say.
Yes.
So I have one question, that means, so when you test it, right, then did you get any real image on occlusion? No?
Yes, right now we have collected the real-time
Okay.
images and I have also tested the model, but I have not added in this particular work because that time we have not collected. But right now we have collected from our institute, and for the next upcoming work, we will include that particularly.
Right, and in terms of the novelty of the network, right, do you have any comment that for that, how your network is novel?
In the particular network, I have used the attention feature, attention module, so that the spatial information will be passed through the training, and that particular convolution which I used.
So the network is very complex, right, very large network, right? That
Yes.
means, so how much time it takes for the training? Have you shown that? Have you got this data?
It's totally depends on the like what kind of GPU we have. So for me, it takes the around 18 hours for the training.
Okay, thank you. Thank you. Okay, so we have the last presentation in this particular session. It's a paper titled Study of Quantifying the Deviation of Remotely Sensed Objects from Multispectral Images, and it will be presented by Pratik Tiwari.
Good evening, everyone. I'm Pratik Tiwari. So I'll be presenting on quantifying deviation of remotely sensed objects or classes from multispectral images. So what we were trying to do is that we were trying to find data of deviation in water bodies and the direction in which the deviation was happening and the direction and the quantity of deviation. So we were unable to find a specific data regarding this. So what we did next was devise the algorithm which could compute this and give us the data. So detection of such deviation has environmental and societal consequences. There are different methods currently. These methods use either complex shape features or use multispectral and hyperspectral images, and along with that, they use maybe machine learning or deep learning. So what I'm going to propose is just a geometric method, and it is very simple. It is using non-complex features such as straight lines, and it can detect the deviation in images having no holes, and this will be done using linear equations. So we can quantify the direction and in multispectral images explicitly. So continuing this, we will first find the object that we are required to change the detective. So here it is a water body. So the image that is shown to you on the left side is actually the water body called Patratu in Jharkhand. So we calculate the normalized difference water index. This brings out the region which has waters around it. So as you can see on the right side, this is the area you get after finding the ratio. After finding the ratio, we can extract the vertices. So these vertices result in the polygon. So the result is a 2D coordinates of water bodies joining these forms the polygon of the water body. After getting the polygons, this polygon can contain a very large magnitude of points. We can perform polygon approximation to reduce the number of points. And what this will do is simplify the computations and reduce the time complexity. So to do that, we use a poly approximation method which has been devised beforehand. We just used that method. Here what we are actually doing is that we are taking a particular value, threshold value, and we are replacing a set of vertices with a straight line, and that straight line is replaced by a straight line when the distance of all those points do not exceed that threshold. So it will be replaced by the straight line. So in the left hand side, you can see a region, this one. So it does not, sorry. So it does not, this region is actually, if you can see, it is kind of straight. So if you give the parameter tau a large value, so it will give you a very approximated polygon. So here on the right side, you can see the approximated polygon. It has been replaced by a straight line. So this is the part explaining the approximation process. So we find the distance delta of the set of points from the polygon side, and those points are retained if their distance is greater than the specified threshold. But if it is not, then they are replaced by the straight line. So this is the polygon approximation. We then calculate the centroid, and on calculating the centroid, there we encounter two cases. So the centroid is calculated as the average of the coordinates. And what our aim is here to find in finding the centroid is that we want the visual center of the polygon itself. So talking about the cases that come when we find the center of the polygon, is that either that centroid will lie inside that polygon, or otherwise it will lie outside. So when it lies outside, we have another set of problems, and we will discuss that later on. But if it lies inside, we use geometric manipulations, and we define a valid solution region. So if there we find the intersection point, then we can quantify the deviation. Okay, there is a deviation in that area. And when we do not find that centroid within that geometric polygon, what we do is that we triangulate that whole polygon. What triangulation actually does is that it divides the whole polygon into a set of disjoint triangles, and those triangles and the property of a triangle is that the centroid always lies within that triangle itself. So these triangles can help compute centroids individually, and all the centroids lie inside that polygon. So even though it does not denote a particular central point of that polygon, but we have points within the centroid which help us calculate the deviation. So coming to the terminologies that I'll be using while explaining the algorithm. So we have two images of the water body at different timestamps, at one at T1 and one at T2. So the T1 timestamp is the earlier timestamp, and the T2 timestamp is the timestamp at some later point of time. Then at the polygon that we form, we call it initial polygon, the one that is formed on earlier timestamp. It has n number of initial points, n number of points, and we denote it by capital Pi. So similarly, the polygon that we form over the water body at the later timestamp T2, so that we call as referred to as final polygon here, and it has n number of points, and we denote the points by small pi. Apart from that, Si here will denote the points of the new the edges of the new polygon, and G will denote the centroid of the new polygon. We will be forming two kinds of line. One will be a line segment joining the initial polygon point with the center. It will detect the inward deviation. If the polygon has shrink, then Pi will detect the deviation, and one would be PG ray, so that will detect the outward deviation. If that over the period of time, the water body has expanded. So coming to the change detection algorithm, if the blue part shows the initial polygon, the red part shows the final polygon, then we have the centroid G. So from each point on the initial polygon, we project lines towards the center, towards the centroid. Now, whenever these points intersect with the new polygon, we find the point of intersection. This point of intersection tells us that there is a deviation happening, and in this case, the deviation is towards inside. So in the third step, we define the valid solution region, that even though a line can intersect that polygon at multiple positions, but the valid solution region is the point where the maximum of centroid and the initial point from which the intersecting line is passing. So the maximum and minimum should hold, like the point of intersection should be within the maximum and minimum range. So that is what here we define the valid solution region. So you can see that there is an invalid solution as well. So that point to P2 cannot move to anywhere around P6 or P5. So even though the line intersects it at an outward position, but it is not a valid intersection point or valid change. So coming to the part if our centroid lies outside of the polygon itself. So in that case, what we do, we can see that here the change detection that we were doing using intersecting lines. So that is not coming through here at all because the region would be around P3 and G, but here we will get an invalid change if we see the intersection on S3. So here what we do is that here we perform the triangulation. On triangulation, we will get such disjoint triangles on the polygon. These triangles contribute to individual central points. These central points then are joined with the initial point, and their intersection gives a possible deviation. So for data generation, we took that water body that I previously mentioned. So it is a still water body called Patratu Lake in Jharkhand. So we have found that an NDWI ratio value, and after that we have generated the polygon. Since at image C you can see that the centroid is lying outside the polygon. So what we do is that we triangulate the whole polygon, and we find the central points of those polygons. So using these points, we find the deviation like we did just in the second case. So here is the data that is generated from taking a central point where it is in the middle. The green point denotes that centroid, and that 2 points we have taken that region and we have tried to generate the deviation for that. So here we have 90 and 129 and 89 and 108. We have zoomed it in the right hand side. So this is polygon approximated for tau is equal to 0.5. Here we have the total data, like whether the deviation was outward or whether it was inward, in what magnitude, in what direction. So we can generate that. Apart from that, we have another region, and we have done the same thing with a different centroid and a different approximation measure, tau is equal to 0.85. We have done the same thing for coal seam fire, and these are the regions that for finding this region we find CMI, coal mine index, and these are regions lighted at fire, and we want to see their changes over time. So for that, we have run the same algorithm, and we have shown that we can find a deviation along the line from P2 to G. So talking about the performance, it is that we are using linear equations, simple linear equations, and geometric manipulations to find deviation in multispectral images. And it can find deviation for any concave and convex shape, given that it does not have any holes. Apart from that, there are a lot of methods which can detect change, but the problem is that we do not find a point-to-point deviation along with direction. So this algorithm can provide that, but apart from that, we have another few problems with that. The water bodies that you will select will never come without holes, or it will either break into parts, like if there is a drying up in a region, so they break into multiple parts. So that will on that kind of a problem, we will have to have some other approach because this approach will not work. And apart from that, yeah, as I mentioned that if we have holes in that water body, then too it will not give concrete results. So that will be all from my side. Thank you.
And the speaker. So any questions from the audience?
So how do you decide the threshold value? Is it, decided by you on your own, or is there any?
For which type?
Polygon approximation.
Yeah, so we take multiple values, like we take a range of values and we see, actually, more you approximate the less accurate results you get. So we are doing it here to reduce the computation, but you can do it, you may not do it.
And like you discussed about the time thing, like whether it's inward or outward. So in real life, will it be possible to, what is the time gap or the time frame? I mean, like if you consider a real life lake or maybe something, then the time duration when the water is, shrinking, it is usually very large. So will it be possible to, apply it in real life?
Yeah, so for this algorithm, we are taking two images at time t1 and t2. So here they are separated by a year gap. What we are doing here, the two images are separated by a year gap. So if you take very images at a very like small instance, then you might not see significant changes. So you might detect some changes, but then the precision error will come into factor because you are running that in a computer in an programming language. So here the code was written in C++. It is available in GitHub. So there was a problem of precision. So if you take two like very close changes, so it will create problems. But for large duration, you can detect it very easily.
Thank you.
Yeah, so the question is, what is the resolution of this detection? That's the question, what she has asked.
Yes, sir.
Okay, that means because normally the changes are pretty slow,
Yes,
right? Unless it is man-made,
yes, sir.
if it is a natural, the changes are pretty slow, right? Due to environmental causes, due to climate change, right? These changes are pretty slow. So how much you can, what is the resolution of this change you can detect with this particular technique?
So I'm glad you asked that question because over here it is limited to the programming language you were using, but I was personally using C++ for this.
No, programming language may not be a constant, I think. Basically the assumptions what you have taken in the problem and how you are making the geometrical rules for this particular problem. Right?
If that is not an issue, precision is not an issue, then you can accurately.
Because too, that is, I am not an expert in this computational geometry, but I think that this the techniques what you have used, right, is pretty standard in computational geometry. It's called, the domain is called the computational geometry, where you can actually extract the object properties, right, through some geometrical interpretation and geometrical processing, right? So only to tell that means you have to really think that what is the real novelty you are trying to come out, right, in this particular technique, and you also have to show some of the quantitative metrics, right, how you tell that okay, the recent techniques of the other ways of deep networks, right, how you go ahead on that.
So the other methods that are being used currently, like there is a median circle method. So it is finding the largest deviation using circles. So what the problem you are facing while comparison is that there is no specific standard metric we could find out on which we could compare the algorithms rather than time being a factor.
Okay.
So deviation for different aspects have different meaning. Like there are algorithms which are finding area in deviation in terms of area. So they will give you a shape, how much is the deviation. But we wanted a quantified result that, okay, so this is 30 meters is the deviation and it is happening in this direction. 40 meters is the deviation, it is happening in outward direction towards 80 degrees. So that is what we wanted to find.
The problem definition is very it's fine. Only the thing I was just thinking that means how you can push your technique right in the next level.
Yes, sir. I would like to add to that. Like you said that the changes are very close to each other. So we are actually using that fact, and we are making another extension to this. We are using closeness as a parameter, and we are using index-based techniques to come up with the next.
Okay. Yeah.
So how do you said you have taken two images of 1 year gap?
Yeah.
So how do you ensure the registration of those two images? Is there any sensitivity of this registration of these two images on your performance model?
Can you repeat?
Registration of those two images.
Registration.
the orientation.
Orientation, so okay, we use softwares for that. I guess QGIS was used to ensure that there is no any rotation or change in, like, there is no orientation change between those two polygons and images.
Because when you are comparing two images,
Yes.
those are both of same orientation.
Yes,
So
so we are using that software to ensure that it is of the same orientation.
Did you foresee any practical application of it?
Yes, sir, practical application.
For example, say you are measuring the area of a lake
Yes,
and how it is changing over the time.
yes, sir.
And the time is about 1 year.
Yes.
Can this method be applied to the flooded area of inundations? Because it is changing every day.
So what, can you repeat louder?
Flat.
Thing is, what is the problem is that the data are very sparse. Only one data at a year.
Yes, sir.
So I'm not thinking of a situation. Say for example, flood is very common in India.
So can you repeat?
Flood.
Yeah, daily flat data, if you see there is a
Got it,
change.
got it, sir.
That's a good
So it
point.
is flood water is changing every day, or every hour.
Every hour change, yeah.
So can it be implemented over
Real
here?
time. Okay, get your question. You want something that is real time.
Because you are talking about the remote sensing there.
Yes, yes.
Remote sensing continuously monitoring.
Okay, I get the question, and that was initially what we wanted to do. So this is the initial paper. After this, what we are trying to do is that I told you, since the changes are very gradual, we are assuming they are not drastic. We are using a data structure, and we are trying to use index-based structures to make it real time. Like what you are saying, if it is in the flood-based region, we want that to be very gradual, so very fast. So that if we are given a list of images, like we are given a huge database of images, we can run on it, and after continuous iterations, we can tell on which direction it is moving.
Right.
Yes. Yeah.
So thank you. So yeah, so thank the speaker. So we end the session here. And thanks to all the presenters and the audience for being in the session and participating. Well, thank you all.
Now request Professor Mola to include the students and Professor Chakravarti. Yes, we end our day. Thank you for joining us. Cultural program starting from 7 p.m.